Welcome back to the online causal inference seminar. Today, we're excited to have Ramesh Johari from Stanford University, who will talk about experimental design in two-sided platforms and analysis of bias. We also have two collaborators in Q&A, so feel free to submit any questions there, Hannah and Gabriel. After the talk, we'll have a discussion by Panos, Toulis. Question today will be handled by Guillaume. So maybe I'm going to switch over to Guillaume for a few seconds.
Thank you, Dominic. So as Dominic said, we're lucky to have Hannah and Gabriel in the Q&A today. So please do submit your questions. Ramesh will also pause from time to time to take questions live. So we'll pick some questions from the Q&A. And if your question is selected, I will ask you to raise your hand and I will unmute you. So please do not raise your hand until I've asked you to do so. All right, that's it from me. Ramesh, whenever you're ready.
All right, is that good? You see it all? Excellent. Okay. Well, first of all, thanks, Michael, Dominic, Guillaume, Hito for inviting me. I've mentioned to many people this seminar has kind of been a role model since the start of the pandemic for how to run a great online seminar. So thank you, and it's really an honor to be able to speak here. I also want to introduce Hannah and Gabriel. The work I'll talk about today is joint with Hannah Lee, Gabriel Weintraub, and Inessa Liskovich. Inessa couldn't be with us. She's a data scientist at Airbnb. Hannah is a PhD student in management science and engineering, my department at Stanford, and Gabriel is a professor at the Stanford GSB. Hannah is actually going to be on the job market in the fall, and it's important for me to say that this really is something that she's driven the lion's share of. Thank you both for being here to answer questions. Okay, so let me just jump right into it. First, just a few words about me, because I know this is a community that I'm perhaps a little bit of an outsider to. My broad area is operations research at Stanford. For the last 10 years, my research has largely focused on market design and platform design, particularly with an emphasis on designing online marketplaces. Oh, sorry, not sure what happened there. So this includes things like search, matching, pricing, learning, reputation. From a practical standpoint, I've spent a lot of time also advising online marketplaces. In the last 5 years, what that's taken me into is a great deal of interest in understanding how these platforms and markets use A/B tests or experimentation to deploy new features. And that's sort of the motivation for the talk today. So when we think about experimentation in two-sided platforms, kind of the mental model I want you to have here is platforms like Airbnb for lodging, Upwork or TaskRabbit for labor, Uber or Lyft for ride sharing. They'll routinely use experiments to test virtually any new feature. Nothing really gets deployed without being tested. Examples of features might be something like, what if we provide better profile descriptions, let's say, for listings or for workers in an online labor market? Or what if you reduce the friction involved in the checkout flow to actually book an item? So in these experiments, kind of the high level point of this talk is first just to emphasize the fact that interference can lead to biased estimates of a global treatment effect of interest. So you're interested in what the market will look like with this intervention rolled out to everyone versus no one, the global treatment effect. And as this entire seminar has studied over the course of the year, interference is a significant challenge in these settings. Okay, and so I will describe in a bit more detail exactly mechanically how that interference arises. At a high level, an important theme in the talk is that there's a very significant connection between the statistical phenomenon of interference and the economic phenomenon of competition. That essentially, there's an inherent connectedness in marketplaces that comes from the fact that if I make one listing more attractive, that'll make other listings relatively less attractive. If I make one customer more likely to book, that will reduce supply available to other customers. So these competition effects on the listing side and the customer side, which are economic phenomena, will be the main drivers of interference in sort of standard experimental methods. As an example, I'm going to use the term customers and listings to refer to the two sides of the market consistently. You could imagine something like an online platform where the listings are freelancers. These are customers. The customers come, they have two stages in which they survey what's going on in the market. First, they consider a set of listings, and then may choose to book something or book nothing at all. And so, I'll get a bit more detail into kind of how we think of this from a modeling perspective later, but that's sort of the mental model I want you to have in mind. So let me first motivate, just to make sure I ground everyone. This slide hopefully is going to feel very natural for people that come from a causal inference background. But I first want to motivate exactly a little bit more this point about how competition can create interference. So for this purpose, we're going to look at a very simple market with just one freelancer and two customers. Okay. Now, suppose I have some new intervention where I'm able to I think I can make customers more likely to book with this intervention. So let's say I introduce this treatment, and the way I test the intervention is that I give some customers the intervention and other customers I don't. So in this example, the green customer is treated, the blue customer is control. Okay. Suppose that customer A arrives before customer B and happens to book this freelancer. In this simple market, which is of course highly stylized, when customer B shows up, there's nothing left to book. Now, the fact that customer B doesn't book isn't necessarily because we're getting an unbiased read of the relative deficiency of customer B's booking flow against customer A's booking flow, of control against treatment. It's really just that there was no inventory left to book at all. So this is an extreme example, of course. In reality, what ends up happening is that when you introduce an intervention that makes some customers more likely to book than others, the treatment customers more likely to book than control, the treatment customers cannibalize listings away from the control customers. And as a result, if you use a naive estimator that just uses the estimates, the number of bookings made by treatment customers and compares it to the number of bookings made by control customers, you'll tend to underestimate bookings relative to global control. You'll tend to overestimate bookings relative to global treatment. And essentially that creates a bias then in your estimate of the global treatment effect. Okay, so this effect here is arising because customers are competing with each other for the same limited inventory on the opposite side of the market when we only randomize on the customer side. More generally, platforms tend to use two types of experiments in a vast majority of these settings. One of them is to randomize only on the customer side. There's, of course, a symmetric version of that where you randomize only on the listing side. Estimates from customer side randomization tend to exhibit interference due to competition between customers. Estimates from listing side randomization tend to exhibit interference due to competition between listings. You might ask, well, is this a big deal? Does this matter in practice? And one of the kind of important motivators for our work is that these kind of earlier empirical work suggested that this bias could actually be as large as the treatment effect. In the case of these two papers, it was in the context of customer side randomized experiments. Coming out of those papers and related work like that, there wasn't really a lot of consensus as of when we started this work on why biases are especially large or what designs or estimators could be used to minimize that bias and variance, specifically in the context of these market platforms. So I've motivated a problem here, which is that I have markets. Markets effectively, the way I drew it on that first slide, looks like a network. The network is creating some spillover effects between treatment and control customers or treatment and control listings. And this whole seminar series has had numerous examples of how we study and model and analyze experimental design and estimation in settings with spillovers that can be modeled through that type of network structure. So what approach would we take if we were to go down that road? A natural way to do that would be to use what's called an exposure model, which is essentially a low dimensional representation of the impact of one unit's treatment condition on, of other units' treatment conditions on a given unit's potential outcomes, all right? This is an approach pioneered in Aronow and Sami in 2013, and then the two references I have here are two leading examples of this approach applied to marketplace experimentation. So I think there's obviously a lot of value in that approach. In this talk, it's going to be quite a bit of a left turn from that typical approach in causal inference. The approach we take is much more structural. We want to know, what aspects of the market impact bias. And I guess I'll just say as an aside, in terms of sort of collision of communities, this is very much, I think, in keeping with the way that the operations research community, operations management community would often study market design and platform design questions. Certainly a lot of the work we've done over the last 10 years that's outside of experimentation, I think, has a similar flavor. which is to really understand structurally, if I give you a market and we have basic sort of understanding of the structure of that market, how can we use our understanding of the market to impact or guide our thinking on experimental design and estimation? So with that in mind, the approach we take is very much more driven by kind of a population model viewpoint, where we explicitly model inventory dynamics, and then we use that model to study interference and bias. And I'm personally, from a research standpoint, very interested in interconnections between these two viewpoints, how we can use structural models to stress test the findings that we get from exposure models, and vice versa, whether or not there are simple lower dimensional ways using exposure models to capture the key features that we discover from a structural modeling standpoint. So, I could, even if the rest of the talk doesn't make any sense, I'd say this is one of the main takeaways that I want to pass along to the audience. I think this is really like the tip of a gigantic iceberg of interesting modeling opportunities in these kinds of settings. For today, my goal is going to be to convince you that there is value in structurally modeling these inventory dynamics, and that we learn something from doing so. Okay, so with that in mind, let me comment quickly on what our contributions are. First, given that previous slide, first, I'd say our contribution is a substrate on which to even be able to study the performance of different experiment designs. And so that's this kind of structural model that we develop, and I'll walk through that in a couple of slides. Now we use that model, and what we find is that there's a particular market metric that has a first order impact on the biases of common designs and their associated estimators. And that is the supply-demand imbalance in the market. And so supply-demand imbalance essentially says, effectively, are there more buyers or more sellers in the market? A market with more sellers than buyers is demand constrained. A market with more buyers than sellers is supply constrained. And what I'm going to try to show you is that we derive, not only are we able to characterize kind of the dependence of bias on this supply-demand imbalance, but also derive a lot of structural insight into why it arises. Beyond that, we're able to use our kind of insights to motivate the development of a novel two-sided randomization design and associated estimators that can actually be used to reduce bias. And I'll conclude the talk with a discussion of major open directions. You'll notice the word inference didn't show up here, which is borderline blasphemous for a causal inference seminar. And that is indeed a very important open direction out of the work that we've done here. This talk is really focused on an analysis of bias. And I'll come back a little bit at the end of the talk to talking about these kind of open directions, of which the most notable omission is inference. Okay, let me just pause there for a second. I don't see any open questions in the Q&A, but if anyone has any questions or anything, take a quick pause. Nothing right now.
I think so far so good. Now I can keep going.
Okay, great. Okay, yeah, obviously just interrupt me, Guillaume, if there's anything I need to chime in on. Okay. So, I've motivated the talk by telling you I want to give you a structural model of a two-sided marketplace. So this is the model that we're going to work with. And again, I will just reiterate one more time that this model is well beyond the typical sort of exposure model that would be seen in a talk in this seminar series. You're going to see that there's a much more explicit stochastic modeling of all the different components that are involved in interactions in these marketplaces. So throughout, if you want an example to attach words to the things I'm talking about, you could think of an online labor platform where the listings, quote unquote, correspond to freelancers. The customers correspond to employers who come book freelancers for some amount of time, and then the freelancers become available again. So with that in mind, I want you to imagine that we'll have n listings, and n is the total size of the marketplace. That's an important scaling parameter in our model. In this picture, what I have is 6 total listings in the marketplace. One of them you'll see is shaded out. That indicates that it's not available to an arriving customer, that it's already been booked by a customer and is currently unavailable. You'll notice that these listings have different types. And so, there's 1 type that's yellow, 3 that are blue, 2 that are green in this marketplace. We don't actually use types in any of our design or estimation. It's just there to allow our model to be heterogeneous, so that essentially it's more general in terms of the structure of utilities and interactions that we can capture. Customers arrive one by one over time according to a Poisson process, and customers are also heterogeneous. They have some type that's indexed by gamma. Okay. Now, when the customer arrives, there's two stages through which we formulate their discrete choice model. The first thing they do is they sample listings from this consideration set, from the market into a consideration set with a probability alpha gamma of theta L. So this probability depends on the type of the customer and the type of the listing. And this sampling is independent across listings. Okay, so essentially, there's a Bernoulli random variable for each listing that governs whether or not each one of these listings that are available are included in this consideration set of the customer. So why do we model it this way? The way we're thinking about it is if you show up to a site, let's say, like Upwork with a huge number of freelancers on the site, Upwork doesn't actually show you all those freelancers, let's say in a search or something like that. It'll show you a restricted subset of those freelancers. So one way to think of this alpha gamma of theta L is that it's that process by which the large amount of available inventory in the marketplace is translated into the actual set that's shown to a customer from which they'll eventually make a choice or not. So that's the second stage of our choice model, which is that a customer chooses from the consideration set according to a multinomial logit model. Okay, multinomial logit is kind of a workhorse discrete choice model, and given kind of the structural modeling we were doing was a natural choice for us to work with. In this multinomial logit model, there's a utility that depends on the customer type gamma, and that depends on the listing type theta. And so the probability of choosing a given listing out of this consideration set is proportional to the utility of that, customer type for that listing type. In this particular case, let's say the customer books the green listing. There's also an outside option, so they may choose not to book at all. And after they book that green listing, the remaining available listings now is that initial available set with the green listing also shaded out. So that's no longer available. Now in the market, of course, if the listings became booked and never became available again, everything would eventually be booked and there'd be nothing left. What we model is that there's an inventory dynamic here where the inventory becomes booked for some amount of time and eventually releases and becomes available again. And so in particular, we assume that bookings of type theta become unavailable for some random length of time and then eventually become available. And that random length of time is exponential. Okay, so the booking dynamics are, there's some available inventory, some booked inventory. Customers arrive one at a time. They form a consideration set. They make a choice that changes what's available in the market as seen potentially by the next customer who arrives, and the cycle repeats again. So I guess the main point to take away from this slide is that this way of structuring the dynamics induces a continuous time Markov chain, specifically with the state vector being the number of available listings in the market. Okay. And what we do then in our work at a high level is that model becomes the substrate by which we are able to study the role of interventions and design and analysis of experiments. So in particular, we consider interventions in the paper that change the customer's choice probability, either through this alpha gamma of theta, which was these consideration parameters, or V gamma of theta that were the utilities. There are three versions you could instantiate of the model that I had on this slide. So one version is the model where you have global treatment. All customers see the intervention on all listings. Another version is global control, where no customers see the intervention on any listings. Okay, so where this alpha and V are the control alpha and V. And then you have an experiment, and I'm going to leave this a bit vague for now, and we'll define it specifically for different experiments, where some customers see the intervention on some listings, and which customers and which listings will be more precise in a little bit. So with this way of thinking about the world, what is a good notion of a global treatment effect? I want to be clear that in real markets, there may be many metrics of interest. In our work, we kind of focus on an important benchmark metric, which is the rate of booking. And so the rate of booking literally would just be what is the rate at which listings are booked over time. And if we have a global treatment version of the model and a global control version of the model, the global treatment effect is the difference between the rate of booking in global treatment and the rate of booking in global control. Okay. So what we want to do, so in an ideal world, what would we love to do? Thinking about it from the model perspective for a second, what we'd love to do is have a version of the model that's global treatment, version of the model that's global control, estimate these rates of booking in steady state, and take the difference. Of course, in reality, there are two gaps here. One of them is that we have to run an experiment on one version of the system to estimate this difference. And the other is that it's a model and it's mismatched to, that it's an abstraction of reality. And so coming back to the main theme of the talk, we want to use the model to derive structural insight into what features of the market or of this model setup are most influential in determining the bias of designs and estimators. Okay. So this is a small interlude just to tell you how, as an operations researcher, we'd approach this type of problem. Inventory modeling, inventory dynamics is an extremely old topic in operations research with a really beautiful set of tools attached to it at this point. This is an example of a model where the continuous time Markov chain is not easy to analyze directly. The steady state distribution depends in complicated ways on the underlying model primitives. And so we use a common approach in inventory model, which is asymptotics, to take some asymptotic of the system, use the asymptotic to study that much more complicated finite Markov chain, or finitely parameterized Markov chain. In our case, what we do is we take a large system or mean field limit. So this is also sometimes called a hydrodynamic or fluid scaling, where we send we send the number of listings to infinity. We assume the fraction of listings, a scaled arrival rate, and a scaled upside option all converge to these deterministic values. Okay. So in the fluid limit, one of the things that's weird, and this gets back to this whole question of inference, is that I'm removing variance. All that's going to survive is the fluid behavior of the system. And that might seem odd, again, for a seminar on causal inference to eliminate all the variance. But I'll go back to what I was saying at the beginning of the talk, which is that I'm focused on understanding bias of these designs and associated estimators. And despite the fact that we eliminate the variance, this hydrodynamic scaling or fluid scaling allows us to still characterize the bias of these different designs. So it's a very valuable structural tool for laying bare sort of how the bias depends on the parameters of the model. Okay. Okay. So here is kind of one mathematical interlude here, just to illustrate how we take our this kind of mean field modeling toolkit, apply it to get a structural model that we can actually handle tractably. What we prove is that as the number of listings in the market, the total number of listings in the market approaches infinity, then the continuous time Markov chain converges in an appropriate sense, and that appropriate sense is uniformly in probability, to a system of ordinary differential equations that can be written down explicitly. And this ordinary differential equation system has a unique limit, the mean field steady state, as t goes to infinity. So we first take n to infinity, then we prove that this limiting ODE system has actually a unique object attached to it, the mean field steady state, in the limit where time grows large. So we think of this mean field steady state as a sort of succinct summary of what that model universe would have given rise to. So as an example, I could have the global treatment model, which is represented by a continuous time Markov chain, take the mean field limit, take t to infinity, it gives me an object I can work with, which is the mean field steady state that comes out of that limiting mean field model. And so in particular, for each of our three universes, global treatment, global control, and the experiment, we have their own mean field steady state attached to them. Now we can express estimators of interest to us in terms of the mean field steady state of the experiment. And that, by comparison with differences between global treatment and global control, will allow us to say something about the bias of different designs and estimators. Okay, so all of this stuff was under the hood. It's basically saying, this is what I meant when I said structural model. This is my way of taking a really complicated set of inventory dynamics, translating them into something that now we can analyze and that we can use to understand the bias of different designs and estimators that we would want to use. So maybe I'll just make one last comment at this slide and then pause for questions. So one of them is, first of all, that we're looking at steady state here, and I think that's an interesting thing to point out because, of course, in reality, experiments are of finite time horizon. We don't run experiments for infinite time all the way out to steady state, which naturally begs the question, sort of what can you take away from a steady state analysis of an experiment? The kind of key point we want to make is that, we're focused on analyzing bias. The platform is typically going to be interested in what the steady state rate of bookings would have been. And so a first readout for us on understanding how bias depends structurally on the design of the market is to compare the steady state performance of the experiment to the steady state behavior in global treatment and global control. So that's one comment. The second comment I want to make is about variance and inference. Although we do all this analysis in a mean fail limit, in the paper we carry out sort of extensive simulation analysis that allows us to also get an understanding of the variance of different designs and estimators. And I'll try to say a bit more about that just a bullet or two at the end of the talk. So maybe I'll pause here. There's a couple of questions. Let me try to answer these. Okay, so isn't the Poisson assumption a problem? Absolutely, the Poisson assumption is a problem. It's a stationary, I'm actually surprised. I'm going to broaden that comment a little bit. Every assumption is a problem in this model. I mean, there's really two very broad philosophical perspectives we can take here. One of them is that every assumption we're making is a progressive deviation from reality. So I would argue there's really no market that perfectly fits the assumptions. And I'm actually not trying to convince you of that fact at all. But from a kind of philosophical standpoint, the approach here is that we're taking a model that we captures enough of the first order effects that are present, notably the role of inventory dynamics and inventory constraints in creating interference, and trying to use that to understand how features of the market are influencing bias. And then, then we need to have additional argument that convinces us the features that we're finding are actually relevant in practice. Okay, and I'll try to convince you of that as I go through the talk. The other kind of point I would make there is that, from a practical standpoint, one needs a full inferential pipeline to be able to make this actionable. And that's something we're kind of actively working on with online platforms to try to actually translate the estimators we develop here into, a pipeline where you actually have standard errors and confidence intervals and all the things you would need to cope with some of the kinds of uncertainties that you're bringing up. And then there's a question about what would have to change to come to a system of PDEs or SPDEs instead of an ODE. Would this be possible? Yeah, actually, it's funny. I think that question is connected to the first one, in fact. The reason we get an ODE is because we have a continuous time Markov chain with a simple state representation. But if you have history dependence, either in the customer arrival process or why they book, or in why listings become available after a given amount of time, all of those things would induce a system in the limit that has a measure valued descriptor rather than a simple state description captured by ODEs. So there are many, many ways the model can rapidly become more complicated if you try to capture more features of reality. I like to tell the following anecdote at times like this. Hal Varian was giving a seminar once, and he put up a model, and someone in the audience said, I actually worked on the same thing, but my model was a lot more complicated than yours. And Hal paused and then said, my model was more complicated when I started working on it too, but then I worked on it for a while. And so, I think like that philosophy tends to be something that pervades a lot of operations research and applied micro, where you're kind of trying to get to a point where your model is capturing enough of the first order effects, but isn't so complicated that you can't do anything with it. That's not to say, though, that I think my personal viewpoint is that a lot of the most interesting things we can do here do absolutely involve taking many more of these practical realities of platforms and asking, what is being missed with the simple modeling approach, and what would we need to do to incorporate that? So those are really good questions. Okay. So with that, let me transition now into the second part of the talk and just summarize kind of what our main results are. First of all, let's talk about two benchmark designs, the two I mentioned at the beginning of the talk: customer-side randomization and listing-side randomization. So customer-side randomization, and I should say, by the way, in the illustrations I give you in these slides, I'm going to assume that listings and customers are completely homogeneous pre-treatment, just because it makes the illustration simple. But that's not an assumption that's needed to go through the work that we do in the paper. Okay, so suppose I have an arriving customer. What does customer-side randomization mean? It means that I have some probability this customer would be randomized to treatment versus control. If they're randomized to treatment, they have some utility V tilde. If they're randomized to control, they have some utility V for a listing. Okay, so this is kind of the key parameter that drives this model. If the customer is randomized to treatment and they arrive to see a market with 5 available listings, they view all of those listings as having utility V tilde. If a customer is randomized to control, they arrive to see the exact same market. they would see that market as having 5 listings with utility V, right? For the illustrations I'm going to show you, I want you to keep in mind a setting where V tilde is bigger than V, so that the treatment is better for the customer, increases utility for the customer, okay? Now notice that what happens here, if a customer arrives as a treatment type and they're more likely to book a listing, they'll take listings off the market. If a subsequent control customer arrives, then that control customer is going to see less inventory in the market as a consequence of the treatment customer's behavior. So this creates this intertemporal interference between customers that's arising because of competition for the same limited inventory, as I discussed earlier. The most common estimator that's used for this kind of experiment in practice is just the naive Horvitz-Thompson estimator, where you look at the steady state rate of bookings by treatment and control customers appropriately normalized by the 2 groups. So here's our first theorem, which is that if you look at that naive Horvitz-Thompson estimator, that becomes unbiased in the demand constraint limit. So on the x-axis here, what I have is relative demand, which is a ratio between the arrival rate of customers and the rate at which listings become available again. And what you can see is that the bias is decreasing as the market becomes relatively demand constrained when lambda becomes much smaller relative to tau. So the intuition for this is actually fairly straightforward. The idea is that interference is arising because of intertemporal competition between customers. So if I can eliminate that intertemporal competition, I wouldn't have any more interference in this type of design and estimation. How do I do that? Well, a simple way is imagine a setting where listings become available again almost instantaneously after they were booked. Well, in that case, when the next customer arrives, the fact that I had booked something will have no impact on the market that they see. So now you'll just have a sequence of customers that are seeing independent copies of the same market with all its inventory available. All right. So in a market where the market's either really demand constrained, so customers arrive slowly relative to the inventory, or the inventory replenishes rapidly, what'll happen is that the customers essentially become decoupled from each other and there's no longer any interference between them. I like to think of this as the Netflix setting. If I watch a movie tonight, that has no impact on whether Panos can watch the same movie tonight. The movies are completely sort of infinitely available effectively from our perspective. Okay, so that's one example. And this result I would imagine is quite robust. So, we've thought about this a bit and we think you can relax a lot of the model assumptions. This result would probably still hold up in pretty much this form. The other side of typical platform randomization is what's called listing side randomization, where a platform will randomize customers into randomize listings into treatment or control. So in this case, what happens is that an individual listing gets a label attached to it, which is that it's a treatment listing or control listing. Now, if a customer arrives, right now the customers are not in treatment or control, it's the listings. Customer arrives and they see 5 listings, 3 of which are labeled treatment, then that customer is going to see those 3 listings as having V tilde as utility, and the 2 blue listings, the control listings, as having utility V. So in this case, what's happening is that when that customer sees that market, then now the customer is going to become more likely to choose a treatment listing over a control listing through that choice model I described earlier. So here there's direct competition between listings in the choice process of a customer. That competition between listings means the treatment condition of one listing will impact the potential outcomes of another listing. So you have interference in the statistical sense, okay? Again, use a naive Horvitz-Thompson estimator, rate of bookings in treatment versus rate of bookings in control. So, for listing side randomization, what we find is the opposite result. And this we found to be a bit more surprising, which is that as the market becomes more supply constrained, then the naive LR estimator, the naive listing side randomization estimator, actually becomes unbiased in that limit. I want to point out a few things. One thing is that this graph here, this is a numerical plot, is plotting bias over GTE, which is the relative bias. In fact, the relative bias may not go to 0 for LR in this limit. The absolute bias goes to 0, but the relative bias may not. And an important point there is that in the demand constraint limit, the CR estimator, even the relative bias goes to 0. So there's kind of a stronger result in the demand constraint limit than in the supply constraint limit. And one of the reasons for this is that kind of the supply constraint limit does depend more on the specifics of the choice model that you use. Nevertheless, this graph is revealing an important insight, which is that qualitatively, LR performs much better than CR in the supply constraint limit. And that we believe to be quite robust, again, through kind of a simple intuition that I can give you, which is if you think about what causes interference between listings, the interference between treatment and control listings arises due to competition between them in the choice process of a customer. So anything that weakens that competitive effect will also have the effect of weakening interference. And as you move into a regime where supply becomes lower, any listing that becomes available is facing reduced competition from other listings, the more you move into a supply constrained regime. So if you face less competition from other listings, that will lead to the phenomenon that there's also less interference, less treatment control interference of the sort that I was describing earlier. So qualitatively, we think it's generally going to be true that LR performs better than CR in the supply constraint limit. This particular result shows that the absolute bias of LR goes to 0 as you move to the supply constraint limit, as you move to the right axis here. Okay, so with the last few minutes that I have, I'm going to talk about a new design, which is two-sided randomization that's kind of inspired by the plot that's on this slide. So you can see that CR and LR exhibit advantages in different regimes of market balance. And maybe I should just highlight here for a second. I opened this talk by saying that it was important to us to find out, to use this model to understand structurally, qualitatively, what features of the market impact bias of typical experimental approaches. And I'd say that these results are examples of that in action, where just a very fundamental market design parameter is the market balance. That's something that anyone who's working in these platforms is going to be acutely aware of. I've worked with these platforms quite a bit, as have Gabriel and Hannah. One thing that we all found surprising is that we were very familiar with that as an important market design parameter, and yet it never really came up in a discussion of what kind of experiment to run. And I thought that one important takeaway of this type of work, this style of work, is that it allows us to connect important desiderata of market design with their impact on A/B testing and experimentation, which I think in general, again, to reiterate that theme, is something that would be very valuable more broadly to develop those kinds of insights. Now, what we wanted to do is recover the benefits of CR and LR in the two extremes. So what we propose is this new design called two-sided randomization, where essentially you randomize customers into treatment and listings into treatment. And now you need to define, well, when is the treatment experience applied? And we take an and of the two treatment conditions to determine that. So if the customer and listing are both in treatment, then the treatment condition is applied. Otherwise, the control condition applies. Okay. This is something that Hito, Pep Bayari, and others at Amazon also had independent work on in 2019 on double-sided randomization. It should be pretty clear that this design generalizes CR and LR, because if you randomize all listings to treatment, then the only randomization that matters is whether customers are in control or treatment. And if you randomize all customers to treatment, all that matters is whether listings are in control or treatment. So you can recover CR and LR as special cases. Okay. So what we did is, we said, here's like a new class of designs you could work with. What estimators are interesting to use here? So, we came up with kind of two interesting ways to leverage design and estimation to deal with the issues of bias that we've shown you so far. One of them, from a design standpoint, is to interpolate between the CR and LR designs. And the other, from an estimation standpoint, is to use competition effects to heuristically debias the estimator. So I think I'll first just point out, that technically speaking, it's not very hard to see that if you design this TSR, if you choose the TSR design and estimator so that you're interpolating between CR and LR based on the market balance, that you can recover kind of the best of both worlds, where the bias is small in both extremes for purple here, which is a TSR estimator, okay? And in fact, you could see that even can offer lower bias in intermediate regimes of market balance than either CR or LR, okay? So that's kind of, I think, clear because of the structure of TSR that we should be able to interpolate. What's more interesting, I think, is that one of the things we initiated is to look at how you can use that TSR design to actually try to deal with the bias that's being introduced. So there, let me just provide a little bit of intuition of how it might be used for debiasing. So what we can do is we can kind of estimate competition effects on both sides of the market, between customers and between listings, using these three control stalls. So here's one way that might look. So let's suppose that the treatment makes a listing more attractive, okay? Which means that if I imagine sort of what bookings should have been made in a world in where I didn't have treatment, from a control and treatment customer's perspective, they should both see controlled listings the same way. So in the absence of any treatment listings, I should have expected that the booking rates in these two cells are about the same. Now, what will actually happen is that because this green box exists, some bookings will be cannibalized away from this cell into this cell. Treatment customers, instead of booking control listings at the same rate as controlled customers are booking control listings, treatment customers will sometimes swap over and book a treatment listing instead. Remember that treatment makes listings more attractive. So by looking at the difference between these two cells, I can estimate the degree of competition between listings in this experiment. All right, so that's CC minus CT. Similarly, I can do something where I estimate the competition between customers as CC minus TC, this cell minus this cell. And in the paper that Hito and Pat Beyer worked on, there's a similar application of these types of correction terms as well. So what we find is that if you use this kind of correction, then this actually allows you to debias beyond just this idea of interpolation. And that debiasing is part of what gives rise to better performance in intermediate regimes of market balance. You're actually able to capture competition effects by leveraging these four cells. And I guess just more generally, I would say that this idea of using creative design on both sides of the market, this is also something which is in the work by Jean Pouget-Abadi and others at Google in their work on bipartite experiments and design there, where one can start to get creative about exactly what kinds of randomization schemes and estimation schemes can allow us to debias. So I want to just close with a couple thoughts, and then I'll open the floor up for Panos. One thing I want to point out is that if you'd come to this talk before and you hadn't seen two-sided randomization, an obvious solution to the problem I'm describing is cluster randomization, where I just take different clusters of the market and randomize them to treatment and control. But one of the challenges in online marketplaces is that the clusters aren't perfectly isolated. You often have a lot of bleed over between customers. For example, an employer who comes to an online labor market looking to hire a web developer may also get some search results that are Python developers or Java developers who happen to also do web development. And that'll in turn interfere with the market for Python development or for Java development. So, we wanted to investigate, well, what are the potential pros and cons of two-sided randomization against cluster randomization? We ran a simple simulation where we had two clusters and we had a parameter that controls the market overlap between the clusters. As you can see, if the clusters are completely non-overlapping, then cluster randomization yields far lower bias than our two-sided randomization estimation would. But one of the virtues of two-sided randomization, we thought, was that even if you get to small levels of market overlap, cluster randomization can start to have bias that's introduced because of these overlaps between the clusters. And that's a situation where TSR, this two-sided randomization and associated estimator, actually control that bias even as the market overlap grows. And this is valuable from a practical perspective because it allows the platform not to have to worry about completely disentangling clusters to be able to run experiments. So this was kind of a valuable insight in comparison with a standard design. I'll kind of only say a couple words about this slide, which is that essentially I haven't said anything about variance. There is a little bit more in the paper, and also more recently in a follow-up paper using a static model on bias, variance, and RMSE related to these designs. But I'll skip this in the interest of time. So looking ahead, I guess to reiterate for the last time, I would say I think like what I'm hoping you'll take away from this work at a highest level is that there's a very different way to look at some of these experimental design and estimation considerations, where our goal is to understand the relationship between market conditions and interference and bias. And looking ahead, there's a lot left to do built off what we've done here. The obvious one was inference, which is to build a pipeline that allows us to estimate standard errors and confidence intervals. I haven't told you anything about optimality. What would be the best TSR designs, and I should say, and estimators that we could construct? And then, another really interesting line of work is to use these new designs to debias existing designs, because platforms are quite fond of running these naive designs. They're easy to run. And maybe one thing they could do is run a TSR design to simultaneously debias many of these naive estimators for LR and CR designs. So a lot of these questions are things we're working on empirically in partnership with live platforms. And maybe more broadly for this community, I'll just highlight that there's a lot of open work left to do in understanding the pros and cons of many different approaches that are deployed daily in these environments to deal with interference, not only TSR, but cluster randomized and switchback and crossover designs. So let me wrap up there. Just went a couple minutes over, but thank you. And let me turn it back to Dominic and Guillaume. Maybe you can tell us what next steps you want to take from here.
Thanks for the nice talk, Ramesh. Yeah, I think we could maybe take one quick question before we switch to the discussion. Guillaume?
Yeah, so one of the questions that was asked by an anonymous attendee is whether for the proposed design it's conceivable that we can do or instead of and for treatment.
Yeah, that's actually a great question. So in this table that I had, you're absolutely right. We could have 3 green cells and 1 blue cell. It is something we've thought about, and you would end up with something very similar, where you could obviously still develop estimates of cannibalization by now comparing across the 2 green cells in each column or in each row. And I think to some extent that choice would require a little bit better analysis of variance in particular, because the main issue that's going to arise there is the change in sample sizes that are rising for the estimates that you're constructing. There's some impact on bias as well, because obviously the cannibalization estimates would be different. But our sort of intuitive thinking on that is that which one of those 2 types of TSR designs you use seems to be more guided by a question of variance. So I think that is one of those questions that's an interesting one to study. You can actually get even more sophisticated, where you have more cells on each side and more complex logic that's applied to determine whether treatment or control conditions are applied on any given edge in the marketplace. So this is definitely just a starting point towards a much richer class of potential designs and associated estimators.
All right, great, thanks. Yeah, then let's switch over to discussion. So Panos presents some slides, and after that, Ramesh, you will be able to respond.
Okay, you can see my slides?
Yep.
Yes, good. Yep. All right, so thanks for the invitation. Thanks, Ramesh, for a wonderful talk. I'm very happy to discuss this paper. I first congratulate the authors. I think it's an important paper. It's very well written. And I'll try to make those points. I'll try to focus on four points, because there's so many things to unpack here, and I feel that even like the 15 minutes is not enough. But I'll do my best. So first of all, one important thing here is that we talk about proper experimental design in competitive markets. It's a new field. It's an exciting field, but it's always important to think about good experiments, good data collection, because this is ultimately what supports also good science. The framework and notation, also another high-level comments. The framework and the notation are really well thought out, I think. And I'm going to discuss a potential outcomes type of formalism, but it doesn't seem to work as well. It does give some benefits, but it seems that it's clear that the authors put a lot of effort in thinking about this clearly and putting it into precise terms. The estimate is interesting because it takes into account this complex system dynamics, which is definitely a complex and interesting task. And finally, we have, in terms of contributions, we have this very insightful, I think, characterization of of the interference and how to deal with it based on this parameter, the structural parameters, lambda and tau. It's a more systems approach to interference. It's different than what we're used to, let's say, in statistics, but it's definitely refreshing and definitely novel. Some quick intuition. So I'm going to be quick about that because Ramesh already presented that. So the problem is that we have, this market over here. We have customers, we have listings, and then our estimate is basically a comparison between these two, let's say, pure treatment and pure control situations, right? In one situation where we treat every customer, we treat every listing, we treat every we have all control customers, all control listings, and then we compare the, let's say, the booking rates between these two counterfactuals. In the experiment, however, it's definitely more messy because there is this interference since these customers are looking into listings that are in control and also looking into listings that are in treatment. So there is a competition between customers for listings. There's also competition between listings for customers. That nice symmetry, I think it's a very nice moment in the paper that symmetry is highlighted in the paper in a very nice way, I think. And an interesting aspect here, I think, is that what we're looking here is that we look into interference as market friction, and I think that's an interesting way to think about interference in this case, because in the case where you didn't have frictions, like the bookings were released immediately, or there are other transactions were kind of very fast and had no cost. We wouldn't have interference. So really, that connection between friction and interference, I think it's new and it's pretty exciting. And actually, the paper does consider those limit cases where friction disappears, right? Like in the case where this release is automatic, we don't have this friction. The customers don't have to wait, and so that friction disappears, and so interference disappears. And that's a novel way, I think, of dealing with interference. It's very different than what we'll do. Hello.
Sorry, I think the slide was frozen on slide 2, but now I see slide 3 again. So,
okay, yeah. So yeah, I was saying that this is a novel way of dealing with interference. Compare this with a statistical approach where we care about, let's say, first order, second order interference effects. We try to position the units in a way, like in the field experiments, let's say, such that we control interference. This is an entirely new, novel way of dealing with interference. So it's definitely refreshing. Now, I think myself, I'm more familiar with potential outcomes, and I guess some of the audience, I think there was a question about potential outcomes as well, like what kind of Sudva violations do we see here? So I think it's instructive to try to express what is happening in this paper through the language of potential outcomes. It's definitely not easy, and you'll see that there are some benefits, but there are some downsides. So this is what the best I could do is, basically, if you write this down in terms of potential outcomes, you will say, okay, the unit is a pair of customer and listing, and suppose there's a superpopulation of customers that come in and go, right? It's not like a constant flow or stream.
I think we're still on slide 3, the intuition slide. It hasn't progressed.
Yes, I have.
Ah, there it is. Yeah, thanks.
Okay.
Now I can see it, yeah.
Right. Yes. So yeah, I was saying that the units are the customer and listing pairs, and then for every customer listing pair at every time t, so some treatments of customers and listings, we have this y, this potential outcomes that tells me whether this particular listing is booked at time t. Okay. And why this is helpful? Because if you just try, you can write down the constraints of the market that will help elucidate, I think, what are the sources of interference. For instance, if you sum up those across customers, then this has to be bounded because listings cannot be overbooked or double booked, right? If you sum up across listings, then again, there's an upper bound because we don't allow overbooking or double booking, depending on the application. And if you just sum up across listings of a specific type, then this has to be upper bounded because we have capacity constraints, this row, I think. So it's not really separated, even though the paper doesn't talk about potential outcomes, it's not really separated a lot by that framework, because you can definitely express those constraints in terms of potential outcomes. And perhaps following that formalism, it has to illustrate where interference is coming from. It's basically potential outcomes, but they have to satisfy some constraints. This is how, I guess, the more potential outcomes people will think about this. And then the estimate is where we take these potential outcomes when everybody is treated, and then when everybody is in control, and then we compare between these two cases. Now, here, what are the benefits of this potential outcomes formalism? I think one is that you clearly see what are the constraints. You can clearly see where interference is coming from. And the second thing is that we can talk about the estimate without even talking about the model. I think this potential point of improvement for the paper will be to perhaps talk about the estimate more quickly, so that it can ground it more formally and before. Right now, the paper kind of talks about the model more. It talks builds up the notation, builds the choice model, and later it gets into the estimate. So I think this is a benefit of the potential outcome in general, that you can very quickly define the scientific problem, and this is also model agnostic, model free. And then you can talk about what kind of models can I use to get there. However, the downside here, and I'm kind of cheating here, is that I'm not telling you what these dots are, and there are other constraints in this system, like the release time constraints, that are just really hard to write down in terms of potential outcomes. So there's there's an upside and downside. So it's but I think it's an interesting connection between the two frameworks. So here's the intuition for the one result in the paper. So you have this customer randomization design. All the listings are in treatments, and here, if this side is like very large, is frictionless, then it's as if the treated customers here, they look into treated units and the treated economy, the full treated economy, and then the control customers is as if they're looking into the full treated economy again, but by definition, this is the same as they're looking into the control economy. So now you have a clean separation, but not by any kind of trick, design trick, or like experimental design trick. It's more like it's a systems, right? It's a consequence of the scaling of that economy, which I think is really interesting. If you want to write this down as a potential potential outcome, so basically what I think what you get is that the potential outcomes is separated into.
Hey, Panos, I think your slides might be stuck again. I think there's some like delay in update.
Yes,
Okay.
now we can see them. Yeah.
All right, sorry. Yes, I was saying that you have, yes. So I was saying that by assuming that this lambda tau goes to 0, it's basically you separate this into two different, let's say, economies, right? So that's why you can get unbiased estimates. And if you want to write this in terms of potential outcomes, which I think is useful, your potential outcomes now kind of separate between a component that's design-based, that's your design, that's the proportion of treated units, and then that part is your estimate. I think that clean separation is a really nice idea, like a systems approach to dealing with interference, where you have the potential outcome, it's separated, and then now for this design part, you can control for it, right? You can do the Horvitz-Thompson estimator, you can get rid of it. Now, this equation here is also a form of Sattva. And there was a question also in the chat about that. It's a form of Sattva because, so the Sattva is not only about the no interference, right? The Sattva is more about the subtle importance of the Sattva is that it tells you what is the invariant, what can you do with very different treatment vectors. And this is exactly what this equation tells you. It tells you that no matter what ZC is, the potential outcome depends on the proportion and the population proportion of this ZC, the customers, the proportion of treated customers, and then the other part is estimate, and that's fixed. And by dividing here, putting this on the other side, you can estimate that estimate. Which I think it's a nice intuition that comes from this system's perspective. Now for the LR design, it's a little more tricky for me, and this is where I struggle a little bit, because in this case where this lambda tau, this structural parameter goes to infinity, essentially we have infinite customers. So no matter what you do,
to progress the slide again. Sorry.
Yeah, so apologies. I think it's because of this AirPlay thingy. But
there it is. Yep, there it is.
Yeah, I was saying that you have we have infinite customers. So in that other regime, the estimate is equal to 0, and that's it's hard for me to think about that. Like it's not really realistic, or at least it's not as realistic as the other setting. And by kind of interpolating our design towards these two extremes, so one extreme is realistic, the other might not be as much. Maybe it's perhaps not the best thing to do. It's a little bit concerning that we're kind of considering settings where the estimate is exactly equal to 0. So I'd like to hear Ramesh's thoughts about that. And a few final comments about, one is about robustness and the other is about other designs. So the paper, the approach to this paper is model based. So it will be nice to know what happens, how would you handle the model assumptions, right? Like for instance, if you solve the Markov chain equations, like in the stationary regime, we get some equations about this booking rates, right? For all of these kind of factuals, but we know that there are some equations that have to be satisfied by these quantities. So what if these quantities? What is the
Sorry,
prediction?
Panos, you have to advance your slide again.
Is it? Can you see now the?
No, we're still on the previous slide.
Okay, I'll do this thing. Can you see it now?
Not quite yet. Now we just see it. It says Panos Toulis has started screen sharing, but we don't see. Oh, now we see.
I'll try that one. Yeah.
Yeah.
Okay, so one question just very quickly is that these types of quantities, the model makes specific predictions about the kind of factuals. So and some of them are estimable, right? So what if these predictions are not validated in the data? What will be the practical recommendation here? And then what if I want to get away from the model assumptions and try to solve simpler questions? For instance, in the stats literature, we don't rely on a model, but we can still test for the existence of interference. Can we solve simpler questions, but at the same time being model agnostic? And finally, regarding alternative designs, that's something that Ramesh also talked about. These lambda tau parameters are crucial. So can I manipulate them directly, like as a platform? Will it make sense? And also regarding these crossover designs, I can put the system in condition 1 and then later in condition 0. Is that better or not? It is reasonable, but is it clear that the TSR design will be better than a crossover design like what I described? And finally, when it comes to cluster designs, to me, it defeats the purpose of the paper a little bit because we're talking about integrated markets. I think this is the main motivation of the paper. So it will be unnatural to think about clustering or a cluster design. So in practice, I will prefer the TSR design compared to a cluster design in this case. But I will be interested to hear more. So that's all I had. Sorry for the technical troubles, but thanks, Ramesh. This is a really interesting paper. It was very fun to read and helped me a lot understand, kind of get a new and fresh perspective into interference, like through this competitive markets.
Thanks, Panos. Ramesh, do you want to respond quickly?
Thanks so much, Panos, for the close reading and the comments. It's really excellent. I'll just add two quick comments. So one is, I said this briefly during the talk, and Panos highlighted it really well. The two extremes are not symmetric in terms of, I would say, how robust our findings are. So CR is, I think, extremely robust in the sense that you could change the model dramatically, and just mechanically, because of the way inventory is turning over, you would still get unbiasedness, or the Sudfa condition that you derived, Panos. The LR extreme is definitely trickier in my view. And I think there's two things I would highlight there. One of them is that the mean field limit that I use starts to break down in that extreme, because in the finite system, you would just have one listing becoming available every once in a while. That's not something you can take a mean field limit of. So there is this commutativity problem in even the mean field limit, theoretically. From a practical standpoint, I think it's the issue that I raised in the talk, that depending on the exact nature of choice, it may not be that the absolute bias goes to zero in that, the relative bias goes to zero in that regime. Nevertheless, so that I don't leave that on a low note, one of the things we did find in this follow-up paper, the work that we've done there, is that the finding that LR is significantly better than CR in that extreme appears to be robust. And that's kind of what I was highlighting in the talk. And the last quick comment I'll make is just, I thought you said something really interesting about what we can do pre-experiment. And that's really, I think, just a huge unexplored opportunity in terms of the kind of the causal inference side of this problem, which is that so much of the interference structure is stuff that we can actually see in advance, because it's really connected to inventory dynamics. And one simple way to look at it is, if I could estimate choice models out of the experiment, and I understood inventory dynamics, I can basically completely recreate global treatment and global control. And so I think, understanding that a bit better, sort of what can be done outside the experiment is like fantastic and fertile ground, connects up a lot with efforts in marketplace simulation as well. So that's a great point. So I'll leave it there.
All right, great, thank you. So I think it's now time to wrap up. So first, thank you so much, Ramesh, for the very nice talk. Thank you, Panos, for a great discussion. And thank you, Gabriel and Hannah, for helping out in Q&A. Next time, we're going to have Razi Nabi from Johns Hopkins University. We're all looking forward to that. Until then, please stay safe and hope you have a great week. Thank you all for coming and see you next time.